So let's consider some examples. Here we have example 1, which is a very simple ODE, first order ODE, y prime equals minus y. So this differential equation, of course, we can solve analytically, but this is a very illustrative differential equation because we can see how different methods perform in a very transparent way, and then we can see how this carries over to more complex equations. So this is the differential equation given this initial condition that the initial value at time t equal to 0 is 1, and we're interested, say, in the solution over the range going from 0 to 2. And of course, we can expect that since y prime, or the derivative of y, is minus 1 times y, whatever the initial value of y is y is going to decay from that value. And as this value reduces, the rate of decay will reduce, and so it will slow down the decay process. And the solution, as we have seen before, exact solution is an exponential solution, e to the minus t. All right? And so we can apply different methods, and so if we apply first order Euler method and integrate the solution out to time 0 to 2, and we look at the graphs of the solution we obtain and compare it to the exact solution and so on, once we do that, we can quantify error using different delta t's. So if we use delta t of 0.2, which means that over a period of 1 we have 5 steps, and over this interval then we are just taking 10 steps. Here we're taking twice as many, 20, and here we're taking 40 steps. So for these delta t's, we can compute the solution numerically, and we can quantify the norm of the error that we obtain. And so this is the 2 norm in this column, 1 norm, and the infinity norm. And there are some very interesting things we can observe here, which is why I made this table here. So as we refine the delta t, as we reduce delta t by a factor of 2, notice what is happening to the error norms. Here was 0.0329, and here is 0.0160. If we double it, because going from here to here, we would be doubling the delta t, and this is approximately doubling. This is about 0.0080 roughly. This is 160. This is approximately twice of this, and this is approximately twice of that, and that's a general feature that all of these numbers have. They are approximately doubling as we double the step size. And so that is what we would expect for a first order method, that the error is proportional to delta t. And so if we want smaller error than the numbers we have over here, if we want more digits to be 0, more zeros we have in the front means more accurate the solution is, the error is that much smaller, then we'll need to refine the delta t proportionately to reduce the error in that way. And so we can compare the behavior of the first order Euler to what we get if we use the second order Euler, or the predictor corrector method that we have described. And so here are the numbers that we get for that. And if we compare the second order Euler with the first order Euler, you can make some immediate trends you can notice. Say even at delta t of 0.2, if we compare these numbers with that, you can see how dramatically the error is reduced. Here this was 0.0329, and this has got 0024. So error is dramatically reduced when we go from first order to second order and so on. So this is a generic thing that will happen as we go to higher order methods. For a fixed step size, the error will reduce. And then even more importantly, as we refine, so from 0.2 to 0.1, this is we have reduced step size by half. Notice that this is not just reduced by a factor of 2, this has reduced much more. If it had reduced by a factor of 2, then 0.0024 would have become 0.0012, but in fact it has reduced by one more factor of 2, 0.006. So actually, if we look at this data more carefully, which is what we will do when we plot it up, we'll see that the error is reducing quadratically with delta t, and that is what we expect for a second order scheme, that the error is proportional to delta t to the power 2. That's why we call it a second order method, and that is what these numbers show as well. So this was the behavior for a linear, the simplest linear first order differential equation. Let's consider a more complex equation next.